All of the nuclear fuel ever used, if put on a football field, would fill the football field and only go up about 30 feet. Nuclear has about a 3 million to 1 energy density compared to other fuels. If you think of it that way, the actual high-level nuclear waste generated in one human lifetime is about the size of a pinball.
This is EnergyCast, and I'm Jay Dowenhauer. Today we are talking about nuclear fuel, the backbone of some of humanity's most technological marvels. As you heard in the cold open, nuclear's energy density is massive. However, it's not perfect, and our guest today is still innovating the assemblies that could power nuclear facilities, even if they are only a few decades young. We've been producing nuclear power almost 70 years, and when you consider that some of the nuclear stations take 15 to 20 years to bring online, consider this technology's history. Fission was discovered by Ernest Rutherford in 1932. The Manhattan Project started in 1942, and in 1951, the first American reactor produced electricity. 3 years later, the Russians opened the first commercial facility. The entire field of nuclear power, the greatest innovation in the history of mankind, went from theory to commercialization in 22 years. So, what is nuclear fuel and how does it work? The most common fuel for power contains uranium dioxide, UO2, a solid that has been processed, compacted into pellet form and stacked into sealed metallic tubes called rods. These rods are then grouped together into fuel assemblies. These assemblies build up the core of the power reactor. It takes a lot of rods, about 200 per assembly and 150 assemblies per reactor. The uranium isotope is 235. In a fission reaction, a neutron strikes this isotope, causing it to become unstable and break apart. This creates heat, and Einstein's theory of relativity is made manifest. As these isotopes split apart, they release more neutrons, which collide into other isotopes, and this causes a chain reaction, resulting in phenomenal amounts of heat, and turbines run off of that. As far as nuclear fuel goes, uranium oxide, or the oxide fuel family, is the most common type of fuel powering reactors around the world. However, our guest is specializing in metal fuels, which forego the pellets and is composed of a uranium alloy or uranium metal. It's long been recognized that metal fuels are much better heat conductors than their oxide cousins, but have been largely ignored because they can't handle high temperatures. Our guest says they've solved that problem, resulting in a commercially viable metal fuel for nuclear reactors that is more efficient and results in less downtime, reducing costs and increasing safety. When I first started working on this episode 9 months ago, I wanted to focus on thorium nuclear technology. So what's that? Well, thorium, other than its cool namesake.
Stop that. I am Thor, son of Odin, and as long as there is life in my breast, I am running out of things to say.
I feel the same way writing some of these monologues. Like the god of thunder, thorium is big. And one of the reasons it's been considered as a possible substitute for uranium is that there's much more of it on Earth, not Asgard. Another reason thorium gets attention is its life cycle. When uranium-235 breaks down, part of it becomes plutonium, which is what the bombs are made of. Thorium breaks down into uranium. Period. So as little plutonium is actually produced in the nuclear power industry, zero is created with thorium. This technology seemed to have a future, but switching to a pure thorium technology, as I understand it, would require new reactors. Our guest today has found a third way, it seems. They've developed a thorium and uranium oxide seed and blanket fuel technology, which they say is fully compatible with existing power plants. So maybe thorium will have its day after all. Our guest today is Seth Gray, President and CEO of Lightbridge Corporation, a nuclear fuel company based in Virginia. Seth has been with the company since 2006, has a law degree and MBA from Georgetown, and serves on the Civil Nuclear Trade Advisory Committee to the Secretary of Commerce. The nuclear sector could sure use more great spokesmen like Seth. I found his remarks thoughtful and fair, and with a public that has mixed feelings about nuclear and its role in our energy mix, I'm glad Seth has cut through the mist to get straight to the facts about this critical component to our energy future. I hope you enjoy my conversation with Seth Gray. We're here with Seth Gray, President and CEO of Lightbridge. And Seth, I'm a big fan of nuclear power. It provides enormous, reliable baseload. It's carbon-free. What else can Lightbridge provide to nuclear?
Lightbridge brings new fuel technology to nuclear that takes the existing reactors or new reactors that are built and makes them safer. The fuel operates 1,000 degrees Celsius cooler than the current fuels in reactors. It won't generate in these what's called design basis loss of coolant accidents, won't generate the hydrogen gas, which is what exploded at Fukushima. It adds a lot of coping time in the event of an emergency, and it makes for much more efficient normal operations of the reactor, where the reactor produces more power. It lasts longer, so it's producing power on days the reactor otherwise would have been shut off for refueling, and this reduces the cost of electricity produced by the reactor. In fact, upgrading an existing reactor with the Lightbridge fuel will result in that added electricity being the lowest cost baseload power on the grid. If you have to add power to an area that already has a reactor, switching to Lightbridge fuel will be the cheapest way to do it. Cheaper than coal, cheaper than natural gas, cheaper than renewables. And Lightbridge also does some consulting services where we bring best practices, very high standards to countries that are thinking of developing new nuclear power programs. We wrote the original strategic plan for nuclear power for the United Arab Emirates, which is running a very successful nuclear construction program leading to first electricity on the grid later this year under very high international standards of safety and non-proliferation and transparency and security. But our focus is on the nuclear fuel.
And that was very interesting, this idea that it's more efficient and that makes it more economic. Is that correct?
Yeah, it's more economic because the reactor's producing more electricity every day, and it's producing electricity on days the reactor would have been closed for refueling. You just don't have to refuel the reactor as often with this fuel.
Is it easy to switch your fuel into a nuclear facility that has been handling something else for several years?
Siemens did a report on this where they go through everything that has to be done, and each of those steps are things that reactors do anyway at times. And all of it adds up to a one-time cost of about $85 million, including the licensing with the Nuclear Regulatory Commission. But for that, you get $60 million of added electricity sales and lower costs from not having as many outages and not having to pay for the cost of as many outages. And all of that work can be done within a normal refueling outage. So the reactor doesn't even have to be shut down one extra day to switch to the fuel.
$60 million per year or over several years? Per year. Wow.
Per year.
Oh, wow. So we can pay back in less than 2 years. All right.
Yeah, it's a pretty good payback.
I want to discuss the disposal policy of nuclear fuel in this country. It's always been a bit of a hot issue, no pun intended. Will we ever see a future where this waste can be processed either on-site or off-site? What do you think about that?
Yes, and France does a very good job of reprocessing their nuclear spent fuel and reusing the uranium in new nuclear fuel and even the plutonium, putting it into new fuel and getting power from it as a way to dispose of it. The United States has a law and a policy against reprocessing fuel that might change in the future. The United States plans to long-term waste repositories like Yucca Mountain, Nevada, that at this point are probably more of a political issue whether they open or not. And in the meantime, the U.S. is storing the spent fuel very safely in the spent fuel pools at the reactor site and in the dry cask storage, as it's called, these concrete storage facilities on the sites where the reactors are. And I suspect in the next few years, the U.S. will probably move that to interim storage sites, which could be at Yucca, which could be at national laboratories, where they just have these concrete casks holding the spent fuel there, and then ultimately into the long-term storage facilities like Yucca Mountain or reprocessing or a combination. Yucca is designed to be what they call retrievable storage. You could put it down there, take some out, reprocess it, use it in reactors. Again, I think it's more of a political issue here in the U.S., and we have the benefit of a lot of land, a lot of space. It's just not a pressing problem. And in many ways, I think a lot of people think it's more of a problem than it really is. All of the nuclear fuel ever used, if put on a football field, would fill the football field and only go up about 30 feet. And that's very little waste volume for how much energy has been produced by reactors. Nuclear has about a 3 million to 1 energy density compared to other fuels. And within that nuclear fuel, only a few percent of it really is what powers the reactor. And within the nuclear waste, only maybe 3% of it is really high-level waste if you reprocess it. Most of it is just uranium you can use again that's not highly enriched. And if you think of it that way, the actual high-level nuclear waste generated in one human lifetime to power a whole lifetime in the West of all energy used by one person is about the size of a pinball. So we're not talking about a lot of waste. It's not an insurmountable technical problem. These things can be handled, and with a 3 million times energy density advantage over other ways of making energy, it's actually just not all that much waste per person.
So do you think that it would make more sense to reprocess it on site than to haul it away? Because it comes in as uranium. Part of it comes out of the process as plutonium, which is pretty nasty stuff. Kind of help us understand and how you avoid that.
Well, first of all, plutonium is very nasty stuff in terms of if you extract the isotopes that are weapons usable, or in powdered forms if you separate it, is just a dangerous material to breathe in or to handle. But embedded within the spent fuel from a reactor, it's not going to hurt anyone. It's in a very safe and stable form and not in any weapons usable combination. If you were to reprocess it like France does, that's done most economically not on the reactor site, but in a central place where the reactors ship away their spent fuel, where it's reprocessed and then reused in making new fuel for reactors to recycle. The United States doesn't have to reprocess. I'm not advocating for it. What we do now is called a once-through fuel cycle, and in future reactors called fast reactors that could run on this waste, that might be a good idea, but we don't have those reactors yet. I think for the United States, which was able to buy uranium from around the world, a once-through fuel cycle makes sense. Reprocessing can make sense as a waste management method, but economically, it probably won't save all that much money versus keep buying uranium for new fuel. But the spent fuel eventually, through reprocessing or fast reactors, will probably be reused in future advanced reactor designs.
Is it as simple as the public doesn't want to have uranium rods shipped to a site and then deadhead back to another location with the spent stuff, or is there more complexity to that?
Well, I think the United States actually ships working nuclear weapons all over the world all the time, aboard submarines and aircraft carriers and on Air Force jets, and we know how to transport and handle dangerous materials. I don't want to compare this nuclear fuel to nuclear weapons. I think the public's problem with transporting it is, first of all, misplaced, because this stuff isn't going to hurt anyone if transported, even if the truck or train got in an accident. But also, I think they'd probably rather get it off their local sites and away to a central place where it'll be stored or reprocessed than stay in their local communities, and for that can overcome any what I think is misplaced fear of transportation.
I initially approached you guys about thorium for nuclear fuel. That's one of the product lines that you have. First off, how serious was the nuclear industry and the government about developing a thorium alternative to uranium?
I think the government was serious. The U.S. and Russian government had some cooperation in the area and were looking into using thorium for disposing of weapons-grade plutonium from the warheads. That program went away without ever disposing of plutonium, along with U.S.-Russia relations not being as good as they used to be. There was also a lot of interest in India that has a lot of thorium domestically and not much uranium, and they wanted to use thorium in reactors, but then the U.S. worked out a deal with India that allows India to buy uranium on world markets. So now the reactors that India is buying are uranium-fueled. And really what the industry in the U.S. and around the world is facing is that the utilities want to always focus on safety and economics. They have to compete with lower natural gas prices, with renewables. So they're focused on technologies that enhance safety and improve their economics. And thorium doesn't really do that. So that's why we're focused on our metallic fuel to enhance safety and to enhance the economics of the existing reactors or new ones. And also with this metallic fuel technology, have less waste and non-proliferative waste that can't be usable for a bomb. But the advantages of thorium were different, including the fear that the price of uranium might go so high it might make more economic sense to use thorium, which is more abundant than uranium. But that hasn't happened, and I don't think that will for some time. And what we're trying to do is meet the demands of the customers. And the customers, the utilities that are advising us, are very clear. They want technology that improves the economics and safety of the current fleet and new reactors, and that's what we're providing. And if there's a change in commodity prices in the future and a change in what the customers want, we can advance our thorium fuel technology again. But right now, it's just not what the customers want.
Is there a future for thorium on a smaller scale in, I guess, what you'd call the non-nuclear countries?
Well, I mean, it could be, but the countries that are new to nuclear power, like the United Arab Emirates, are using uranium fuel cycles. They're doing it very safely under international safeguards and using very non-proliferative technologies with uranium fuels. So I think that there can be a place in the future for thorium, although some of that is more the types of reactors that people are looking at that could use thorium fuels, and some of those reactors could also use a uranium fuel, not just a thorium fuel, and there'll be a question as to which fuel makes the most sense. But yeah, I could see in the future thorium having some interest in certain countries, but we'll see. Right now, that's not the case.
You mentioned the United Arab Emirates, and I wasn't ever really clear on what's the threshold for bringing a certain country into the nuclear family. How does a country become nuclear?
What you see is that the countries work very closely with the International Atomic Energy Agency and with the countries that provide nuclear reactors and end up putting in a lot of infrastructure over time. And all of this happens under the Nuclear Non-Proliferation Treaty, and it really ties these countries very strongly to the rest of the world in nuclear power. And it's a big effort by a country. I think the experiences of those who have been entering lately, particularly the United Arab Emirates, have been very positive in showing just how well these countries can deploy new nuclear programs.
When we were talking earlier about thorium versus uranium, you were saying that there was a fear in the past that uranium prices would go up, and that hasn't really happened. So how secure are uranium supplies, and how certain are you that the price of uranium is going to stay steady for the foreseeable future?
Well, first of all, the fuel cost is generally only about 4% or so of the total cost of owning and operating a nuclear power plant. Most of the costs are capital costs. And of that 4%, only a little over a quarter of that is based on the price of mining uranium. There's also conversion, enrichment, fuel fabrication. So the price of uranium itself is only about 1% of the cost of owning and operating a reactor. And uranium is an abundant element. It is in countries around the world in enormous quantities, in Kazakhstan, in Australia, in Canada, just massive quantities. There's uranium in the United States. But I don't think anyone has a fear of sort of uranium supplies being cut off. There's enough diversity of supply from different countries. There are mines that haven't even opened in Canada where they know there's more uranium. I don't think uranium will end up being a bottleneck in the deployment of new reactors. And if at any future date that were to happen, you could go to reprocessing spent fuel and reusing it as a fuel for reactors. There is a very long-term supply of material available.
one of the things it seems is that everything involved in the locus of the nuclear plants seems to be about 4 times more expensive, Seth. Even the same equipment, the serial number has a -N on it, and it's more expensive. And is that good for nuclear, or do you think that there are things that we could do to bring down some of the operational cost of nuclear? What do you think about that?
Well, the utilities have been doing a great job at managing their costs. The N stamp on certain items that comes from ASME, the American Society of Mechanical Engineers, is not just a very high quality stamp, but it's something that shows the nuclear safety culture. For example, diesel generators cost more with their N on them. They start up much quicker than the same generator that is of commercial grade, and that's part of the nuclear safety culture. Now, it's possible with new approaches like the Lightbridge fuel that buy a lot more time. You might not need as much redundancy in some of that equipment, and there might be some savings there. But overall, the cost of generating power in a nuclear plant over the life of the plant is very cost competitive, and in many places is the lowest cost electricity on the grid. I think the public, if they would go and visit the plants and meet with people from the company, would be very happy with the stress on the safety culture and really see nuclear for what it is, as the safest industry in the country. No one's ever died in the history of this entire industry in the United States from a commercial reactor. Not one worker, not one member of the public. It's an extremely safe industry.
In a previous episode, we discussed small modular reactors, particularly the ones that NuScale is working on. How do you feel about those?
Oh, fantastic. I think NuScale has designed an excellent small reactor. They're in the process of getting the licensing from the Nuclear Regulatory Commission, what's called the design certification. They've been supported by the U.S. Department of Energy. It's just a remarkably safe design. Their fuel designer and fuel provider is Framatome, which is Lightbridge's partner in a joint venture called Envision for making fuel. And we're in some discussions for the future of using Lightbridge fuel in a NuScale reactor. They'll start out with the current, what's called uranium dioxide fuel, and that's what they're licensing with the NRC now. But I think we could even help improve the economics of that plant with Lightbridge fuel. And overall, we think that NuScale is going to be a big success for the U.S. nuclear power industry.
Last question. Do you feel like there's a public perception or confusion about nuclear power? And what do you think that is? And what would you really want people to understand that you think is getting lost in the public discussion?
Well, I think that most people do support nuclear power. That's certainly what the polling shows, and that the support is most strong in the communities where the reactors are located. And the workers at the plant come from the local community, and they just know the safety culture and how safe it is. I think that some of the perceptions of radiation dangers or proliferation issues from nuclear are issues that the public needs to better understand, but I think will, as new nuclear projects are proposed. Also in a world that is very concerned about air pollution, very concerned about climate change, having this massive generation of electricity from a plant that contributes nothing to air pollution, contributes nothing in terms of climate change gases from that reactor. I think the public's going to start to realize that actually the benefits of nuclear power are fantastic, and some of the fears they've had have been way overstated and can be addressed as well with new technologies like the Lightbridge fuel.
Fantastic. Seth, I'm going to let you go, but first I'd like to finish with the lightning round of your thoughts on different energy technologies. The first one is natural gas.
Very important to American energy, reducing CO2 emissions and pollution versus coal, but in the end produces half the CO2 of coal, so switching to more nuclear will then mitigate that.
Crude oil.
It seems that transportation is heading toward electrification, and that also is an opportunity for nuclear as well as natural gas and others. I think we'll be moving away from petroleum in the transportation sector over time, which is the biggest part of the demand for crude oil.
Nuclear.
A very safe, carbon-free, pollution-free means of generating electricity. There's a lot of new technology that's very exciting, like NuScale, like Lightbridge coming along, and watch this space. There'll be a lot of good news in nuclear power.
Coal.
something that has lifted millions of people out of poverty here and in other countries. Coal powered the Industrial Revolution. Coal has problems of CO2 emissions, of other pollutants, and perhaps we can have some carbon sequestration and storage and better scrubbers, but it seems that the coal industry will only recover so much.
Wind.
Very good in the locations where it makes sense. It only produces power when the wind is blowing. There is no economical battery storage yet to levelize that. Perhaps there will be someday, but I think that wind generally caps out like solar at most 30% of generation in one area based on when the wind blows and when the sun shines. So even with wind in places that have a lot of wind, most of the power needs to be supplied by other sources.
And then on the flip side of that, solar.
Again, in places where it makes sense, it is good to use, but again, it's very limited in terms of how much energy it can produce and what times of day it can produce it. So wind plus solar at times, with nuclear running at other times, or natural gas seems to be the kind of combinations we're heading for in generating much of our electricity.
Biofuels.
Not CO2 emitting, but they tend to be a lot more expensive, and perhaps for airplanes, perhaps for ships at sea, but in terms of transportation in cars, I don't think we'll see a lot of biofuels beyond the ethanol that's already used.
Hydroelectric.
Generally has been very good, non-pollution emitting, non-CO2 emitting. However, most places in the world that could have efficient hydroelectric dams already do. It's very hard to add a great deal more hydroelectric. In some places with pumped storage, as it's called, hydroelectric can act as a backup to renewables like wind and solar. But for the most part, hydroelectric is tapped out of how much can be deployed in the world.
Geothermal.
We have a lot of energy under us in the earth. It seems enticing to try to capture it, but it's actually for any given square foot of land, not all that much geothermal energy under you. So again, where it makes sense, tap into it, but I just don't think we'll see major cities powered by geothermal.
Electric vehicles
seem to be coming, and sometime in the next decade or two probably make more economic sense than petroleum-fueled vehicles. And I think they are the wave of the future, and pollution and CO2 emissions will depend on what's the power source used to charge those electric vehicles. If it's nuclear, if it's hydro, if it's renewables, then that's clean. If it's burning carbon, then there will still be those CO2 emissions into the atmosphere.
Energy efficiency.
Great, and conservation is wonderful. There are limits to how far we can go in a world where about 1 billion people have no energy supply at all. But efficiency will always help. It will always be environmentally a very responsible thing, but it will always be very limited what it can contribute as well in a world that just needs massive energy supply.
And then finally, nuclear fusion.
It seems is always 50 years away, no matter what year you're looking at it in. We are hopeful for nuclear fusion in some future decade, but the technology is still so far from being perfected and being able to be deployed at a commercial scale economically that I think at this point, like at every point for the last half a century plus, saying it's about 50 years away, and maybe 10 years from now people might say it's 40 years away, but we'll see.
Okay. Seth Gray, Lightbridge, thank you so much for your time.
Thank you, Jay. Appreciate it. Great being on with you.
That was Seth Gray, President and CEO of Lightbridge Corporation, a nuclear fuel firm. Seth says we can expect an announcement this year for Lightbridge Fuel and an American nuclear reactor. As I mentioned earlier, I've worked for the better part of a year on a guest for this topic. So special thanks to Dr. Jonathan Cobb at the World Nuclear Association in London for pitching Lightbridge as a guest. Also big thanks to both Seth and Natalia Rudman at Crescendo Investor Relations for helping to set this up. Hope we can work together in the future. All guests are sent the completed and raw audio the week of release. So far, no complaints. You can find plenty of pics and information on Instagram at Host Energy and online at energy-cast.com. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 33. Be sure to join us next time when we learn about the fastest way to get oil and gas around underground. Until then, I'm Jay Downhauer. We'll see you next time.